next example, I'd like to look at carbon dioxide. And you'll see that we'll in fact extend the rules that we're going through because this situation is a little bit more complex. So starting off, first of all, I'm going to count the total number of valence electrons. So carbon contributes 4, oxygen 6, 2 times 6. We have a total of 16 valence electrons. I make a skeleton. And again, I don't put carbon and then oxygen and oxygen. As I say, we tend to put the least electronegative element in the middle. And again, the atom that occurs only once in the middle. I connect the atoms with the dashes, which again represent a pair of electrons. And then I put out enough electrons to give an octet to every atom. And if you verify, you'll see that oxygen is surrounded by 8 electrons, carbon by 8 electrons, and then the other oxygen by 8 electrons. I then count the total number of electrons that were required to give the octet, and I can see that I've used 20 electrons. So clearly I've had to use too many electrons. Now you might be wondering, well, why would you do that? Why would you put out too many electrons when you now are going to just have to take them away? Well, that's the point. We intentionally put out too many electrons to make it very clear that more electrons are needed than we actually have. And yes, I'm going to have to erase some electrons. And I'm going to notice how many pairs of electrons that I need to erase. So physically, I'm going to erase 2 pairs of electrons. And one of the things I'm going to comment on is for every pair of electrons that we erase, so for every pair removed, or in excess if you will, it equals 1 additional bond. So what I mean by adding an additional bond is essentially you're going to be taking that single bond, that dashed line, and you're going to be adding another line. So an additional bonding pair bond type of electrons. And the idea here is that this will result in a double bond. Now if you have to add 2 additional bonds, well then that could result in a triple bond. So for every pair of electrons removed, you're going to have to add 1 additional bond. Well, in this case, I had to remove 2 pairs. So 2 pairs removed. That means I have to, in a sense, add back 2 bonds. Now, it's not that those bonds come from just anywhere. They have to come from a pair of electrons. And so you're going to see here that essentially what we're going to do is we're going to take 1 pair and another pair, and we're going to, in a sense, place them between the carbon and the oxygen. Place them between the carbon and the oxygen. And such, we'll be making 2 double bonds. 1 double bond between 1 carbon and oxygen, 1 double bond between the other carbon and oxygen. So it will look something like this. I predicted that those double bonds would be there because I had to use too many electrons to give an octet to all the atoms. I had to take away 2 pairs of electrons. That means I had to add 2 additional bonds. Therefore, I'm going to have 2 double bonds in this case. Now you'll notice that the oxygen is surrounded by 8 electrons. So 2 bonding pairs, 2 lone pairs. The carbon is surrounded by 8 electrons. And in this case, it's 8 electrons involved as bonding pairs. So here I have apparently drawn the Lewis structure for carbon dioxide. If I count the electrons, you'll see indeed it's 16 valence electrons. Every atom has an octet. I am now done. But you see this indeed involved an extra step. Now I argue that this approach to drawing the Lewis structure in a sense is foolproof. You make a skeleton, you add enough electrons to give an octet to every atom. You see if you actually have enough electrons to accommodate those octets. In this case, we didn't. So we had to take 2 pairs away. That implied that there were going to be 2 additional bonds in the form of our double bonds. At this stage, I ask you to consider practicing with these 3 molecules. You may wish to stop the video and then I'll go through them with you. So here's what the Lewis structure would look like for diatomic chlorine. Let me talk you through the process. So the idea is that first of all, we would determine the total number of valence electrons. In this case, we have only chlorine. Chlorine's number of valence electrons is 7. 2 times 7 is equal to 14 valence electrons. I make a skeleton, so I put those together like that. and then I put out enough electrons to give an octet to all the atoms. And indeed, you can see in so doing, I have actually used 14 electrons. And so we are done. Again, this is rare that it works out just perfect the first time you do this. So now let's look at oxygen. And for reference, here is the answer. But let me show you how we got there. So total number of valence electrons. In this case, each oxygen contributes 6 valence electrons, and so I have a total of 12 valence electrons. I make a skeleton. I put out enough electrons to give an octet to every atom. And in so doing, and now I'll actually write down here, we would have used 14 electrons, as in the example above. So I had to use an extra pair. Well, as I mentioned, for every pair, every extra pair that you use, it equals 1 extra bond. So I'm going to actually physically remove a pair of electrons, and then I'm going to make that extra bond with one of these pairs. So I'm going to stick it in here. And indeed, that leads to our Lewis structure right here. And then finally, let's look at the solved answer for nitrogen. So you can see that there's a triple bond holding those two atoms of nitrogen together, and that can be arrived at, again, very systematically. Total number of valence electrons is equal to, now each nitrogen is contributing 5, so 10 electrons. I'm going to make a skeleton. I put out enough electrons to give an octet to every atom. As you might imagine, this would involve using 14, as was the case in the previous two examples. So of course, that's 2 extra pairs of electrons that I needed to make an octet. So I'm going to physically remove those extra that I put in. And so for every pair, an extra bond. So I use 2 extra pairs, which means 2 extra bonds. Now the only place to put those 2 extra bonds is actually between the nitrogens. Now again, I can't just write in an extra pair of electrons. So I'm going to physically drop that pair in there and drop that pair in there so that I end up with this structure right here. So I hope you found that these examples are relatively straightforward. We're going to apply these ideas to more complex examples. Before we do that though, I'd like to talk you through a little detour. And this detour is necessary for you to understand the outcome of our next example. So in this detour, I'm showing you the Lewis structure for some common hydrocarbons. Now you might be wondering, well, how are these Lewis structures? There are no Lewis dots. Well, in this case, the carbon bonds are in a sense saturated. There are no lone pairs of electrons. So we've got ethane, we've got ethene, which you might know as a so-called plant hormone that assists in ripening. And then we have ethine, which is used in blowtorches, so it's a good fuel. So we have examples of a carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond. So one of the things that I'd like you to notice first of all are the formulas. And we'll be coming back to this when we study organic chemistry. So in this case, it's C2H6. And in a sense, for 2 carbons, those 6 hydrogens are the maximum number of hydrogens that you can have for 2 carbons. But of course, if you have a single double bond, and that sounds a bit weird. If you have 1 double bond between the 2 carbons, you have C2 and then H4. So the fact that we've reduced the number of hydrogens actually tells us that we can't have just single bonds in the structure. So as I mentioned, 2 carbons, the maximum number of hydrogens are 6. And if you don't have those 6 hydrogens, well, then there must be something else going on there. And then finally, we've got C2H2. So for 2 carbons, only 2 hydrogens implies that indeed there must be some extra bonds. In other words, a triple bond in this case. Now, I'd like you to take note of how having these extra bonds between the carbon impacts the bond energy and the average bond length. Now, as you might imagine, the bond energy has to do with the energy required to break the bond. And essentially, we're asking, well, what's the energy required to break a single bond, a double bond, and a triple bond? And in the key questions there, you're asked to make a conclusion. Well, hopefully it's fairly obvious to you. With an increase in the number of bonds, there's an increase in bond strength. But actually, I still find this kind of remarkable that all we did is draw some of these Lewis structures, and then we can predict, well, yeah, of course, the ethyne is going to have a stronger carbon-carbon bond because we're predicting it to be a triple bond. The other main conclusion that I hope you notice is that as the number of bonds increase between two atoms, it actually shortens the distance between those atoms. So the average bond length gets shorter, and this will always be true. Now, I hope you recall that the PM stands for picometer. So, of course, we're talking about very small lengths. So the carbon-carbon single bond around 154 picometers, and then down to 120 for the carbon-carbon triple bond. So in particular, remember this last conclusion that the bond length, or the average bond length, decreases with more bonds between the atoms.